Problem number 32 in Chapter 2 of Rizzoni is an interesting problem. It states that there's a 220-volt electric heating device that consists of two resistive coils that can be used to provide 4 different power levels by connecting them either individually, in series, or in parallel. And we're asked to determine the resistance of each coil. We're told that the maximum power setting is a 200 or a 2,000 watt setting, and the minimum power setting is 300 watts, and the other two power settings will be somewhere between 300 and 2,000 watts. So here's the deal. We've got two resistors, call them R1 and R2, that can be connected to 240 volts either individually, or they can be connected to the 220 volts in series with each other, or they can be connected to the 220 volts in parallel with each other. And each of those different connections then will give us one of 4 different powers. All right, how do we pursue this? Well, we know that power is equal to I times V. And we know from Ohm's law that when we're dealing with resistances that V is equal to I times R. We're given voltage, we're given power, we're asked to determine the resistances. So we can eliminate I from these equations by solving this equation right here for I, where I is equal to V over R, and then substituting I in this equation with that, so that we get P is equal to V over R times V, or V squared over R. Now, this R is going to be either R1 or R2, or the sum of R1 plus R2, the series combination, or the parallel combination. So we know that the maximum power, P max, is going to equal V squared over the resistance that leads us to the highest power. Now in this form we see that power is inversely proportional to R. What that means is that the larger R is, the smaller the power will be. Or conversely, the smaller R is, the greater the power will be. So we'll have a maximum power when we have the lowest or the smallest possible resistance in the circuit. Now, what do we know? We know that when resistors are connected in series, let's call that R sub S, the resistances simply add R1 plus R2. And we also know that when the resistance is connected in parallel, call it R sub P, that's equal to R1, R2 over R1 plus R2. Further, we know in this form that the parallel combination of two resistances is less than the resistance of either of the resistors individually. And in series, the resistances add, so the series resistance is larger than either of those two resistors individually. So R sub P, the parallel combination, gives us the smallest value of R, which when we plug into this formula here gives us the largest value of P. So P max then will be equal to V squared over R parallel, which we know P max is 2,000 watts. So we have then that 2,000 watts is equal to V squared, which is 220 volts, squared, divided by R sub P. Solving for R sub P, we get then R sub P, which is equal to R1 R2 over R1 plus R2, must then equal 220 squared divided by 2,000. So just taking this, multiplying both sides by R sub P, dividing both sides by 2,000, gives us this. And with a little help from the calculator, we find then that R1 R2 over R1 plus R2, which is equal to this, is equal to 24.2 ohms. So the parallel combination of R1 and R2 is going to equal 24.2 ohms. Similarly, the minimum power is going to equal V squared divided by the largest resistance possible, which is R series, R sub S. And we're told that minimum power is 300 watts, will then equal 220 squared divided by R sub s, which leads us then to R sub s, which is just equal to the sum of the two, R1 plus R2, will equal, solving this for R sub s by dividing both sides by 3,000 and multiplying both sides by R sub s, gives us then R sub s, which is equal to R1 plus R2, will equal 220 squared divided by 300. And again, the calculator tells us then that that's going to equal 161.3 ohms. So we now have two equations in two unknowns. One is that R1 over R2 plus R1 R2 over R1 plus R2 is equal to 24.2 ohms, and the sum of the two resistances R1 plus R2 is equal to 161.3. So solve that however you will, solve that system of equations however you will. Perhaps the easiest way is to just replace, or to solve this equation here for one or the other. Let's solve it for R1 then by subtracting R2 from both sides. R1 is equal to 161.3 minus R2. Now we're going to take this expression for R1 and plug it into this equation right here. So we have then R1 R2 over R1 plus R2 is going to equal 24.2. So substituting in this expression for R1, we get then 161.3 minus R2 times R2 divided by R1 plus R2, or 161.3 minus R2, that's R1, plus R2 equals then the 24.2 ohms. The R2's in the denominator add to 0, leaving us 161.3 in the denominator here. So multiplying both sides of the equation by that 161.3, we get, in the numerator one, or on the left-hand side, 161.3 minus R2 times R2 is equal to 24.2 times 161.3. Distributing that and cleaning this up just a little bit gives us 161.3 R2 minus R2 squared is equal to approximately 3904, dropping the decimal places. Alrighty, we have a quadratic equation. There's going to be two different values for R2. To solve this, we get all the non-zero terms on one side of the equation and then plug it into the quadratic formula. When we do that, first of all, we get R2 squared minus 161.3 R2 plus 3904 equals 0. Now you can plug that into your calculator and use the solve option, or get the quadratic formula out, and when you do that you get two values for R2. R2 equals either 29.65, or the other value is 131.68. Now it turns out that from this, one of these values is the value of one resistor and the other is the value of the other resistor. So R1, or R2 is that then, and we'll just say that R1 is that. Those then are our answer. And you can take those and you can plug them in and calculate the parallel resistance and the series resistance. Series resistance is pretty easy. You can just go ahead and add those up and you'll see that you get the 161.3. Parallel, you get the 24.2, and plugging them in to our original power equations, you'll see that those two values do lead to the maximum power and the minimum power.